In this problem, we use the stiffness method to find member forces for a coplanar, that is 2D, frame. The key concepts we'll use are calculating fixed end forces for frame members and calculating frame member forces given deformations. And here's our frame. It's the same structure we used in the example problem for section 3 of chapter 16, where we calculated the structure stiffness matrix. And it's also the same structure we used for the other problem for section 4, where we used the structure stiffness matrix to find deformations and reactions. We went through those examples first because we need the structure stiffness matrix to find deformations, and we need those deformations, shown here, in order to find the frame member forces. So for this structure, we're going to determine the member forces at the ends of each frame member, specifically for node 3. The cross-sectional area, moment of inertia, and modulus of elasticity are identical for both of the members and are provided. And here's our approach. We picked a determinate frame so that we can find these member forces by using just the equations of equilibrium. And we did that because when learning a new analysis method, either a hand method or computer method, we should always first use it on a problem for which we know the solution. That way we can confirm that we understand how to use the method properly, or if we're developing a method, we can confirm that the method works properly. So that's how we'll start. Then, to use the stiffness method, we'll calculate member forces. And then we'll compare. Alright, let's get started. So we begin with step 1. Let's find the member forces. By equations of equilibrium. Start by finding the reactions. We have a reaction at degree of freedom 7, a reaction at degree of freedom 9, and a reaction at degree of freedom 8. So if I sum moments about node 1, this one, take counterclockwise as positive, we get a negative contribution from the lateral force applied through the height 12 feet. We get a negative contribution from the uniform distributed load acting over 12 feet, and its resultant is 12 over 2 from node 1. We get a positive contribution from reaction at degree of freedom 7 acting through 12 feet. I solve for the reaction at degree of freedom 7 and I get a positive 17 kips up. Now let's sum forces in the x direction. Choose to the right to be positive. We have a positive contribution from the reaction at degree of freedom 8 and a positive contribution from the lateral load. Solve that for the reaction at degree of freedom 8, and we have a negative 5 kips. And now let's sum forces in the y direction. And we'll choose up to be positive. We have the reaction at degree of freedom 9 minus the distributed force acting over 12 feet plus the reaction at degree of freedom 7, which is 17 kips. I'll solve that for the reaction at degree of freedom 9, and we get a positive 7 kips. That is acting up. And this was negative. It is not to the right but to the left. Now let's find the member forces at node 2. First for member 1. And so let's draw a free body diagram of member 1. It is 12 feet tall. This is the near node, and this is the far node. So we have near and far, which means that my unknown member forces are QF x prime, QF y prime. X prime axis is denoted going from near node to far node and extending beyond. And our moment at the end, QF z prime. We also have our reactions that we now know. 7 kips up, and we drew it to the right, but it's a negative 5 kips. This is the top of member 1, so the concentrated force does not show up on this free body. We'll begin by applying equilibrium along the x prime direction, which is up, and we have a positive 7 kips vertical reaction and the unknown member force Fx prime. Solve that for the unknown member force, and I get a minus 7 kips. Then I sum in the y prime direction. To the left is positive. I have a negative contribution, but a negative 5 kip magnitude from the reaction, and my unknown Fy prime. I solve that for Fy prime, and I get a negative 5 kips. Now let's sum moments about node 2. That's the far node. Choose counterclockwise as positive, and I get a contribution from the reaction, the horizontal reaction, and as drawn would be a positive contribution but a negative magnitude through 12 feet, and to which I add our unknown Fz prime. Solve this for our unknown member force Fz prime. We get a positive 60 foot kips. Now to find the member forces at node 2 for member 2. And I'll draw a free body diagram of member 2. It is 12 feet long. This is our near node. This is our far node. So we have near and far, which makes my unknown at the near end y prime, the shear, near node x prime, and drawn counterclockwise, near node z prime, the moment in the member. We also have a uniform distributed load of 2 kips per foot and a vertical reaction that we calculated to be 17 kips. So let's apply equilibrium, and we'll start with forces in the x prime direction, and that will be to the right is positive because x prime goes from near node to far node and continues on. So we have nx prime, and that's the only contributor, so it's 0. Then I'll sum forces in the y prime direction, and so up is positive. We have our unknown ny prime minus the 2 kip per linear foot distributed load acting over 12 feet plus the 17 kip reaction at the right end, which means that ny prime is a positive 7 kips. And now let's sum moments about node 2. That's this one. We'll choose counterclockwise as positive. We get a positive contribution from the unknown moment at the left end, the near node. We get a negative contribution from the distributed load acting over 12 feet, and its resultant acts at a distance 12 over 2 feet from node 2. And we get a positive contribution from the 17 kip reaction acting through 12 feet. We solve this for the unknown nz prime, the moment at the end of the member. We get a minus 60 foot kips. And now step 2. Let's calculate member forces, and let's do so using the stiffness method. So to calculate member forces using the stiffness method, member forces are given by little q, and so that's local coordinates, k prime, which is the element stiffness matrix in local coordinates, lowercase d, the deformation of the degrees of freedom for the element in local coordinates, plus the fixed end forces in local coordinates. And this equation is given by 16-1 shown here. The only piece that is missing is the addition of the fixed end forces in local coordinates. But I don't know the deformations in local coordinates. I have the deformations in global coordinates, and these are in degree of freedom order sequence. So I need a way to convert those, and we do so this way. We'll substitute in for lowercase d here using the transformation matrix, capital T, times the deformations in global coordinates. And this expression is given by 16-3 shown here. Let's start with member 1. We need to begin by finding the deformations in local coordinates. We're going to do that by transforming the deformations from global coordinates Remember, these are an increasing degree of freedom sequence. These will not be. To create the transformation matrix, we need two pieces of information. We need lambda x, which is calculated by taking the change in x coordinate as we go from near node to far node of member 1, and so that's going to be a 0 divided by the length of the member, and so lambda x is 0. Lambda y will be obtained by taking the change in y coordinate from near node to far node, 12 feet, divided by the length, so lambda y is a positive 1. Reminder, our expression is given here, and so our sequence is near node x, near node y, near node z, which is the rotation, far node x, far node y, far node z. And through this equation we'll end up with near node in local coordinates, so x prime, near node y prime deformation, near node rotation, far node x prime deformation, far node y prime deformation, and far node rotation. And then we evaluate the transformation matrix, or we assemble it. Remember, lambda x is 0, lambda y is 1, and so we have minus 1, because it's minus lambda y, lambda x, zeros, zero for lambda x, 1 for lambda y, minus lambda y, lambda x, and a 1. Now our deformations in global coordinates. Near node x is degree of freedom 8, and we'll have 9 and 5, then 1, 2, and 3. One, 2, and 3. So when we pull those deformations from here, 8 and 9 are 0. 5 is a minus 5.27 times 10 to the minus 3 radians. 1 is a 0.636 inches. 2 is a minus 1.159 times 10 to the minus 3rd inches. And 3 a minus 2.72 times 10 to the minus 3rd radians. Now if you compare these deformations to the values we calculated in the last example problem, you'll notice a slight difference. And that's because I recalculated them using more significant digits. So I minimized the round-off error and its effects on these quantities. So now let's finish our transformation. Our deformations in local coordinates for member 1 will be, we have 0 and then a 1 times 0, a negative 1 times 0, and then 1 times the negative 5.27 times 10 to the minus 3rd radians, and then a 1 times the negative 1.159 times 10 to the minus 3rd inches, then a negative 1 times our other displacement, so we have a negative 0.636 inches, and then a 1 times the negative 2.72 times 10 to the minus third radians. We also need, for member 1, fixed end forces in local coordinates. And so I draw a free body of member 1, near node, far node. We have the fixed end forces at the near node and fixed end forces at the far node, but there's no load applied to this member and there's no imposed horizontal displacement of the far node relative to the near node. So all of my fixed end forces for member 1 are zeros. Now it's time to actually calculate the member forces for member 1. So we're going to find the near node force in the x prime, that is the axial, the near node y prime, which will be shear, near node z prime, which will be moment, far x prime axial, far y prime, which is shear, and far z prime, which is moment. And to calculate that, we need the K prime matrix, which we saw in equation 16-1. So to assemble the K prime matrix, we need AE over L, 12EI over L cubed, 6EI over L squared, 4EI over L, and 2EI over L. All of these quantities we had calculated in the example for section 3. So if we go back to our notes from section 3's example where we assembled the structure stiffness matrix, AE over L for member 1 is 6,042 kips per inch, and then for K prime the next two entries are 0, and we have minus AE over L, and then the next two entries are 0. Our next row consists of 0, 12EI over L cubed, 6EI over L squared, 0, minus 12EI over L cubed, and then a positive 6EI over L squared. Which means for member 1 we have 0, 81.6 kips per inch, 5874 kips, 0, minus 81.6 kips per inch, and 5874 kips. Our third row, 0, 6EI over L squared, 4EI over L, 0, minus 6EI over L squared, and 2EI over L. So for member 1, that's a 0, 5874 kips. 4EI over L is 5,63900 kip inches. Then we have 0, minus 5874 kips, and 2EI over L is 281900 kip inches. Our next row is exactly the opposite of the first row. Minus 6042 kips per inch, 0, 0. 6042 kips per inch, 0, 0. The fifth row is exactly the opposite sign, same magnitudes as the second row. And so we have 0, minus 81.6 kips per inch, minus 5874 kips, 0, a positive 81.6 kips per inch, and a negative 5874 kips. Our last row is a 0, 6EI over L squared, 2EI over L, 0, minus 6EI over L squared, and 4EI over L, which gives us 0, 5874 kips, 2EI over L, 281900 kip inches, 0, minus 5874 kips, and 4EI over L, 563900 kip inches. Let's take a moment to check for silly mistakes, and we'll do that by checking that our diagonal are all positive entries. They are. And that it is symmetric about the diagonal. These are the same, the 0 and 0, and these two zeros, and the zeros in the corner, the minus 81.6, these two, positive 5874, the negative 5874s, this one's the diagonal, these two, and then these two, the two zeros about the diagonal, and then these two. So it is symmetric. We multiply this by the deformations in local coordinates, which we calculated and assembled here. So we have a 0, 0, minus 5.27 times 10 to the minus third radians, a minus 1.159 times 10 to the minus third inches, a minus 0.636 inches, and a minus 2.72 times 10 to the minus third radians, and to which we add the fixed end forces in local coordinates, which are all 0 for member 1. So now let's multiply these matrices in order to find the fixed end forces. We start with this term times this deformation, which is 0, and a 0 times a 0 times this deformation, and then this one times this deformation. So we have a minus 6042 kips per inch times minus 1.159 10 to the minus third inches. Then this will be 0, this will be 0, and we add the fixed end force, which is 0. So that's all that contributes to the member force QNX prime. Next row, 0 times 0, 81.6 times 0, and then we have these two contributing times the minus 5.27 times 10 to the minus third radians, 0, this term times this term, So we have a minus 81.6 kips per inch times the minus 0.636 inches, and this term plus 5874 kips times the minus 2.72 times 10 to the minus third radians, and then we add our second row of the fixed end forces, which is 0. Now our third entry, we'll get 0 out of this quantity, the 5874 times 0, and then this quantity times this, 5,63900 kip inches times the minus 5.27 times 10 to the minus third radians, 0 times this deformation, and then we have these two multiplying, 5874 kips times the minus 0.636 inches, and then these two, 281900 kip inches times the minus 2.72 times 10 to the minus third radians, and we add the third row of the fixed end forces, which is 0. Fourth row, or fourth term here, this will be multiplied by 0. These zeros, the 0 times this deformation, and then we get contribution from these, 6042 kips per inch times the minus 1.159 10 to the minus third inches, 0, 0, and add in the fixed end force, which is 0. Our next entry, we'll get 0 contribution from this term, this coefficient times 0 deformation, then we get contribution from this pair, minus 5874 times minus 5.27 10 to the minus third radians, nothing from this deformation, and then this term times this term, 81.6 kips per inch, the minus 0.636 inches, and then this term times this term, 5874 kips minus 2.72 10 to the minus third radians, and then we add in this fixed end force, which is 0. Last row, this won't contribute anything. This one times 0 does not contribute. Then we get from this pair times the minus 5.27 10 to the minus third radians, nothing from this deformation, and then these two multiply together. We have the minus 5874 kips times the minus 0.636 inches, and then this last pair plus the 5,63900 kip inches times minus 2.72 10 to the minus third radians. We add in the fixed end force of 0. When we multiply these out, add up and subtract all the terms, we get the following internal forces, or member forces, at the ends of member 1. We get a positive 7.0 kips, a positive 5.0 kips, a negative 2.6 inch kips, a minus 7.0 kips, a minus 5.0 kips, and 716 inch kips. Now, of these 6 member forces, it is the far degrees of freedom that are associated with node 2. So it is these, or are these quantities that we were asked to find. Now to repeat the process for member 2. So we need to begin by finding the deformations in local coordinates. And that's given by transforming from global coordinates using the transformation matrix. And we said in order to do that we need to have lambda x for the member, and member 2 goes from near node to far node, so the change in x coordinate is 12 feet, its length is 12 feet, so lambda x is 1.0. Lambda y is the change in y coordinate, which is 0 divided by the 12 feet length. Lambda y is 0. And so our deformations will be in local coordinates: near node x prime, near node y prime, near node z prime, which is a rotation, far node x prime, far node y prime, and far node z prime, which is also a rotation. The transformation matrix we have in equation 16-3, and so with lambda x 1 and lambda y 0, we get the following transformation matrix. So our transformation matrix became the identity matrix. All zeros except the diagonal, which is ones, which means that the quantities we have here, the deformations in global coordinates, will be unchanged. So the implication of that is when the local coordinate system, x prime, matches the global coordinate system, x, then these are already in local coordinates. But a reminder, these are not in the degree of freedom order we need for the element. Our capital D is in increasing degree of freedom order sequence. And so for our global deformations in the x direction at the near node, we have degree of freedom 1, and then we'll go to 2, 3, 6, 7, and 4. And so let's write those in. 0.636 inches minus 1.159 10 to the minus third inches minus 2.72 10 to the minus third, 0.636 inches, 0, and 1.88 10 to the minus third radians. And so when we transform these, we get exactly the same back. Minus 1.159 10 to the minus third inches minus 2.72 10 to the minus third radians, 0.636 inches, 0, 1.88 10 to the minus third radians. Now we need the fixed end forces for member 2. And remember, those need to be in local coordinates. So let me draw a free body of member 2. This is our near node. This is our far node. So we have near and far. It's 12 feet long. We have uniform distributed load of 2 kips per linear foot. And we have, for fixed end forces, near y prime, near x prime. Remember, x prime is from near node to far node, passing through it and continuing on. And the moment at the end, near z prime. At the far end, we have y prime, x prime, and z prime, the moment. So if we look at the inside back cover of our text, we find that the moment at the left end is given by omega L squared over 12, because we have fixed, uniform distributed load. The moment at the other end will also be omega L squared over 12, but it is not drawn counterclockwise, so it will be negative. So we have omega L squared over 12, which is 2 kips per linear foot, 12 feet length squared over 12, so it's a positive 24 foot kips. Q at the far end, and these are all with the subscript not, because they are fixed end forces. And so getting back to our calculation, for the far end, fixed end force will be minus omega L squared over 12, so it's a minus 24 foot kips. And we're going to need to convert these to the same units that our stiffness coefficients use, which are inches and kips. So if I take this quantity and multiply it by 12 inches per foot, I'll get a positive 288 inch kips. And here we'll get a negative 288 inch kips. Now along the axis of the member, since the load is applied normal to the member, these are zeros, and to find the y prime values, I'll need to use equilibrium with our free body diagram. So I will sum moments about node 3, which is the far node for this member. Counterclockwise will be positive, and so we have the positive 24 foot kips at the near node minus the contribution from the y prime force acting through 12 feet plus the contribution of the distributed force acting over a distance of 12 feet, its resultant acting at a location of 12 over 2 feet from node 3, plus the contribution of the far end moment, which is minus 24 foot kips. When I solve that, for the near node y prime member force, we get a positive 12 kips. Now let's sum forces in the y prime direction for this member, up being positive in this case, we have the 12 kips at the left end minus the 2 kips per linear foot acting over 12 feet plus the far y prime, oops, forgot our knots there, y prime fixed end force. Solve that for my fixed end force and we get a positive 12 kips also. So when I consolidate these, near x prime naught, near y prime naught, near z prime naught, far x prime naught, far y prime naught, and far z prime naught, our fixed end forces for member 2 in local coordinates are 0, positive 12 kips, 288 inch kips, far x prime 0, far y prime a positive 12 kips, and far z prime a negative 288 inch kips. So now we are ready to calculate the member forces for member 2. So we'll calculate the near x prime, which is axial, the near y prime, which is shear, near z prime, which is moment, far x prime axial, far y prime shear, far z prime moment. And to do so, we need the element stiffness matrix in local coordinates, little k prime, given in equation 16-1, and so we needed several quantities that have already been calculated in example 3, where we assembled the structure stiffness matrix. So starting at the first row, we'll need AE over L and minus AE over L. And for member 2, that's 6042 kips per inch. We have a 0, a 0, then the minus 6042 kips per inch, 0, and 0. The second row, 0, 12EI over L cubed, 6EI over L squared, minus 12EI over L cubed, 6EI over L squared. For member 2 is 0, 81.6 kips per inch, 5874 kips, 0, minus 81.6 kips per inch, and 5874 kips. Third row, 0, 6EI over L squared, 4EI over L, 0, minus 6EI over L squared, 2EI over L. For member 2, those are 0, 5874 kips, 4EI over L, 5,63900 kip inches, then a 0, minus 5874 kips, and 2EI over L, 281900 kip inches. Then the fourth row is exactly the same as the first row, but all signs reversed. So we have minus 6042 kips per inch, 0, 0, a positive 6042 kips per inch, 0, 0. The fifth row is exactly the same as the second row, all signs reversed. 0 minus 81.6 kips per inch minus 5874 kips. 0, 81.6 kips per inch and minus 5874 kips. Then our last row, 0, 6EI over L squared, 2EI over L minus 6EI over L squared, 4EI over L. 0, 5874 kips, 2EI over L, 2,81900 kip inches, 0, minus 5874 kips, and 4EI over L, 563900 kip inches. We multiply this by the deformations in local coordinates, which we found here. And so we have 0.636 inches minus 1.159 10 to the minus third inches minus 2.72 10 to the minus third radians, positive 0.636 inches, 0, and 1.88 10 to the minus third radians, and to which we add the fixed end forces in local coordinates, which we calculated here. So we have 0, 12 kips, 288 inch kips, 0, 12 kips, and a minus 288 inch kips. So let's perform the matrix multiplication. Our first row, we have this term times this term. .636 inches. We get no contribution from this term or this term, and we have this term times this term, negative 6042 kips per inch, 0.636 inches. No contribution from this term or this term, and then we add in the fixed end force, 0. Next one, no contribution from this term. We multiply this one by this one, 81.6 kips per inch times the minus 1.159 10 to the minus third inches plus this term times this term, 5874 kips times minus 2.72 10 to the minus third radians. Nothing from this term. This one times a 0 contributes nothing, and then we have our last term, 5874 kips times this deformation, 1.88 10 to the minus third radians, and then we add in the 12 kips fixed end force. Now our third member force. Nothing from this term. This one times that term, 5874 kips times the minus 1.159 10 to the minus third inches plus the product of these two, 563900 kip inches times the minus 2.72 10 to the minus third radians. Nothing from this term. This coefficient times this deformation gives us 0, and then we have the product of the last one, 281900 kip inches times the 1.88 10 to the minus third radians, and then we add in the fixed end force 288 inch kips. Our fourth member force, we have this coefficient times this deformation, minus 6042 kips per inch times the 0.636 inches. Nothing from this term, nothing from this term. Then we add this coefficient times this deformation, plus 6042 kips per inch times 0.636 inches. And then we add the fixed end forces, which is 0 for this one. Our next member force, nothing from this term. We have the negative 81.6 times this deformation, negative 1.159, 10 to the minus third inches. We have this term times this deformation, minus 5874 kips times the minus 2.72, 10 to the minus third radians. Nothing from this term. We have this coefficient times 0, contributes nothing, and then we have the product of these two, minus 5874 kips, 1.88, 10 to the minus third radians, and then we add in our fixed end force, a positive 12 kips. Now our last member force, nothing from this term. We have the product of this times this deformation, 5874 kips times a minus 1.159, 10 to the minus third inches. This coefficient times this deformation, plus 281900 kip inches times the minus 2.72, 10 to the minus third radians. Nothing from this term. This coefficient times 0 contributes nothing, and then the product of these two, 563900 kip inches times 1.88, 10 to the minus third radians, and then we add in what is a negative fixed end force, 288 inch kips. Once we evaluate each of these expressions, we obtain the following member forces. These add up to 0. Then our next term, a positive 7.0 kips, a negative 722 inch kips. These add up to 0. A positive 17.0 kips, and a negative 0.5 inch kips. For this member, these are the degrees of freedom, the near node that belong to node 2. Now step 3. It's time to compare results of member forces for node 2. Let's start with our stiffness method results. For member 1, we have Qx prime, Qy prime, and Qz prime, which we found to be minus 7 kips, minus 5 kips, and 716 inch kips. So we have a minus 7.0 kips, minus 5.0 kips, and the 716 inch kips, if we divide by 12 inches per foot, give us a positive 59.7 foot kips. Member 2, Qx naught, Qy naught, Qz or y prime and x prime. So the axial at node 2 in member 2 is 0, the shear plus 7 kips, and the moment minus 722 inch kips. So we have 0 for axial plus 7.0 kips for shear, and if we convert the 722 inch kips to foot kips, we get a negative 60.2 foot kips. Now the results we obtained by using the equations of equilibrium. For member 1, axial, shear, and moment at node 2 were minus 7 kips, minus 5 kips, and a positive 60 foot kips. And a positive 60 foot kips. For member 2, axial, shear, and moment we calculated to be 0, 7 kips, and minus 60 foot kips. When we compare these, they match almost exactly as we would expect, and the slight difference is due to round off. But the magnitude of the difference is well below 1%, and usually I can live with an error below 1%. So we have a reasonable result. Now let's go back and review the process we followed. We chose to use a determinant structure so that we could calculate all of the member forces using just the equations of equilibrium, so that we would have something to compare against at the end to ensure that we understand how to apply the direct stiffness method properly. So we began by finding the reactions for this frame, then the member forces at node 2 for member 1 and member 2. We then used the stiffness method to calculate member forces. Starting with member 1, we use the transformation matrix to convert deformations in global coordinates to deformations in local coordinates. We also found the fixed end forces in local coordinates. We then assembled the element stiffness matrix in local coordinates, that is K prime, multiplied K prime times little d, the deformations in local coordinates, added in the fixed end forces, little q naught, and obtained the member forces for member 1, and we identified which of those were associated with node 2. For member 2, we repeated the process, but we observed that when the local coordinate system matches the global coordinate system, the transformation matrix becomes the identity matrix. We calculated the fixed end forces for member 2 using information from the inside back cover of our text and equilibrium. We then assembled the element stiffness matrix in local coordinates, little k prime, performed matrix multiplication and addition, and obtained the member forces for member 2 and identified which of those were for node 2. We then compared the results from the stiffness method and from applying equations of equilibrium and found them to be an almost exact match. The slight difference is due to round off. Well done.